So, good morning. We are Group 7. We are Laura Parra, Laura González, Alexis Rodriguez, Daniel Rosso, and Julián Pulido. We are going to present the agitation project that we made. So, the aim of our project is to understand and design an agitation device using CFD software with the purpose of determining its power curve. Furthermore, what we want is to design an innovative geometry so it can generate at least the same amount of shear stress in comparison to a Ruston standard device, or ideally generate more shear stress than the standard turbine. Why do we do this? Agitation has been a very important unit operation throughout chemical history, being present in devices such as continuous stirred reactors or mixers, providing a greater grade of homogenization for the species that are being treated. That's why understanding such unit operation is important to improve the processes of chemical industry. The first part of our project consisted in the dimensioning and of the tanks for both the Ruston and the innovative design that we made. The software inventor was used prior to the simulations to be able to perform a correct dimensioning. Here we see the standard measurements for a Ruston. The idea was not to surpass in our design the dimensions of the Ruston. So we see that it has a height and a length of 14 centimeters. The baffle thickness is set to 0.4 centimeters. The baffle width is set to 2.5 centimeters. And the most important physical constraints regarding these topics are the width of the impeller. It must not have a greater width than 10.4 millimeters, and it must not have a greater diameter for the impeller than 51 millimeters. The next slide exhibits the results that we obtained on the software inventor. We finally achieved a diameter of 50.24 millimeters and a width of 8.5 millimeters. At the right, we can see the standard Ruston impeller with the physical constraints and dimensions that I previously mentioned. The innovative part about our geometry is the tooth-like structures. What we want with the tooth-like structures located at the top part and the bottom part is to achieve greater mixing or homogenization of the fluid or species that are being treated. After the inventor part, the geometry was exported to StarCCM to be able to perform the simulations. The most important procedure was the meshing. Meshing is important because it allows us to characterize appropriately the geometry to be able to perform correct simulations. Polyhedron mesh was established because it enhances computational time. It allows lower Skinner's calculations, lower residual values, and more homogeneous geometry in comparison to tetrahedral or hexahedral meshing techniques. At the end, 560,000 cells were obtained for the innovative turbine using a basis of 2.2 millimeters on the impeller. This cell number was the one that was expected. We were expecting a number of more or less 500,000 to be able to minimize computational costs and not having simulations that would last too long. After the meshing procedure, we have to set like the simulations that we want to do. So 6 different simulations were established, each one with a unique Reynolds number and a unique angular velocity. We see that the change in Reynolds number defines the flow regime that is being studied. And we see that, for example, that we have a Reynolds number of 1 for an angular velocity of 0.0038 revolutions per second, and the last one is a Reynolds number of 100,000 and an angular velocity of 38.44. Additionally, what we wanted to prove is the performance of our design with a non-Newtonian fluid and a Newtonian fluid. That's why the 6 simulations were ran for both water and mineral oil. The first important results that we wanted to exhibit was regarding the power of the procedure. The number power was obtained in function of the Reynolds number. That's what we see at the both graphs that we have in this slide. In the first one, the one on the left, we see a comparison between the theoretical value of the number power for the Russian, and in the orange line we see the real results that we obtained for the rest. We see that more or less the same behavior is obtained. The form of the curve is more or less the same. We see that for higher Reynolds, we have a decreasing number power. And to be able to measure like the misfit between the two approximations, we calculated the root mean square. We obtained a root mean square of 9.3. Root mean square should be close to 0, but a value between 0 and 10 is more or less reliable because we can attribute that 9% of the whole variability explained by both curves is explained by the error. In other words, the error is only influencing 9% of the misfit. On the other hand, we have the MP curve for our design turbine. We see that more or less it is the same behavior that we obtain at the left, with the difference that we have lower values. This implies a better result, implying that we are wasting less power in the procedure with our design device. The next important result is concerning the shear stress. As said earlier, we wanted that the shear stress would be at least the same of the Western or greater than the Western. What we achieved here is the first result. We were able to generate an innovative impeller that had at least the standard results that a chemical industry expects. That's why we see that both curves are very similar. They are very close to each other. Finally, we tested the Newtonian versus non-Newtonian. We know that, for example, for a Newtonian fluid, the relationship between shear stress and shear rate is linear. That's precisely what we obtained for water, which is the graph that we are seeing in slide 10.
Now, with respect to the velocity and flow profile, we can observe in this figure that these profiles are very similar between each other. The only difference lies in the fact that the shape of the region with higher velocity is different. In the case of the design impeller, it has a strange geometry where in between the blades the high velocity liquid is less radially spread. In conclusion, it can be said that the objective of this project was fulfilled, since it was possible to create a turbine in an innovative way, which was compared effectively with the Russian turbine. On the other hand, it was possible to compare the theoretical Russian with the simulated in CFD by means of the NP for the impeller design. The MP was lower, which means that it presents a lower energy consumption than the Russian.